circles. Well, what's a circle? What's most important to understand about a circle is that they have centers, by definition. And the center of the circle is the point that is the same distance from all the points of the circle, which means that from the point of view of construction, which we will do repeatedly throughout the chapter, that when one constructs in a set of radii into a circle, and we will start to do that today, we know that they're all equal in length, just by definition of circle, okay? And that opens up so many avenues of inquiry, because typically what you get are triangles, very often isosceles triangles, and then we know an awful lot about triangles, about isosceles triangles. So that's like the description of the general strategy of the chapter. All right, but there are a few matters, this is 1 and 2 and 3 and 4 up on the board, that I want to talk about just to review very quickly. Clean this up. Really the point of entry into the chapter that I called a bridge before, that allows us to make use of results from previous chapters in this chapter, is the concept of a central angle and an assumption that we made about central angles. So the basic idea is this. There probably is a circle tool here, but I'll just draw my own. So let us say that we have a circle, and that C is the center of this circle. Then a central angle is an angle. There's two ways to put this, probably more than two, but here are two. The vertex is the center of the circle. That's one way. A second way, the sides are radii. And what we assumed is this, is that the degree measure, call that alpha with the degree symbol on it, is the same as the degree measure of the arc. So we will also talk about degree measures of arcs. And what do we mean when we talk about the degree measure of the arc? We mean that it is the same as the degree measure of the central angle that cuts that arc. And again, cuts just means is inside of, okay? So that's like the bridge. That's the fundamental connection that allows us to take what we knew in previous chapters and apply it to this chapter. There were some other results as well that will be absolutely crucial in later chapters. That's the number 2 that's on the board. So this was central angles. The number 2 is that diameters cut semicircles, okay? And what's meant is this. Let's say that we have a diameter. And please remember the correct definition of diameter. It's not the longest chord. Well, it is, but that's not the definition. The definition is chord through center. And then it's provable that diameters are the longest chords. As a matter of fact, you prove it on the worksheet. So let's say that we have a diameter, which means a chord through the center. One result is that the arc that is cut by this diameter, that is, the arc that shares its endpoints, will be 180 degrees. And well, actually, of course, there'll have to be 2 of these, one on one side, one on the other. And this is provable. And I talked on Friday about how it is that one would prove this, and it's really very simple. A diameter is also a central angle. It's a central straight angle, of course, because diameters are straight. And what's the measure of a straight angle? Quick, 180 degrees, right? And again, the fundamental connection here in this chapter is that the measure of the central angle is the same as the measure of the arc. So immediately we get that a diameter cuts an arc of 180 degrees, which is what we mean by a semicircle or a half circle. And it goes the other way around as well. That is, if one were to have a circle, and let's say that we were to have 2 points on it, a point A and a point B, and we knew that the arc that stretches from one to the other is 180 degrees. If that was the given, then if we create the chord, notice I said chord, from A to B, then it's provable that this chord is also a diameter. Okay, and I won't review the proof of that, but that is one of the results that gets proven. So diameters cut semicircles, and any chord that cuts a semicircle is a diameter. And those will be important results. And then finally, number 4, this will be important in this chapter and also important in later chapters as well, says this, or like the short version says this, it says that circle centers are unique, okay? So we know that a circle has a center. Let me make really explicit what that means. We know that every circle has at least one center, which is a point equidistant from all the points on the circle. But that definition by itself, that is the definition of circle, which guarantees the existence of the center, doesn't guarantee that the center is unique, okay? That is, it does not guarantee the definition that that center point that is guaranteed by the definition of circle is the only point that is equidistant from all the points in the circle. And then one of the results that I had you prove does then actually establish that a circle cannot have a second center. That is, there could not be another point inside the circle like this D point that's also equidistant from all the points in the circle. As a matter of fact, what you prove is that there isn't even a point that is equidistant from 3 points on the circle. And if there's no point other than C that's equidistant from even 3 points of the circle, then there's not one that's equidistant from them all. So the center is really unique. Another way to put the point is this. Sometimes this will be the really helpful way to put the point. Let's say that we have a circle and a circle. Notice that I didn't say a circle and another circle, or a circle and the same circle. I just said a circle and a circle. Maybe they're the same, maybe they're different. If that circle and that circle intersect at 3 points, really that's the same circle twice over. Okay? You cannot have two distinct circles that intersect at 3 or more points. Okay? 3 or more points. And this will actually be crucial at various points along the way, both in this chapter and later chapters, because we'll be at work at a problem and we'll know that we have a circle and we have a circle. And it's like, oh, okay, so it turns out that each of these go through the points A and B and C. And then at that point, we will be able to immediately say, oh, it's the same circle twice over. Okay, that is, the circle is equal to the circle. And that will be important. All right, so let me hop over now to the next section, which is section 9.2. And this is a set of fundamental results about circles. And let me say this. I know it is the case that, sorry, I wasn't actually back at the start. I know it's the case that many of you have avoided myriad problems that involve circles because you figured that you didn't know enough about circles yet because we hadn't done the circles chapter. Fair enough. Though I do suspect that many of you did know enough about circles to do this because you didn't have to know much. However, once we get the first really 4 sections done in this chapter, you'll know like absolutely everything that you need to know to do all the circle problems on the myriad. Doesn't mean they're easy, of course, but you'll have all the background knowledge that you need. And that's lots of problems. So hopefully you'll feel that lots of problems are now open to you. Okay. All right, so let's prove some basic results, or at least talk about how they're proven. So first one, if in a circle you have equal chords, then those equal chords cut arcs of equal measure. Let's make sure that we understand what this says. You've got to know the language here. A chord is a segment. Chords are straight. Okay, and what makes them chords is that their endpoints are on the circle. So what's really been said here is this, is that chord DE and chord BC are equal in length. And what we will conclude is that their associated arcs, for one arc BC and the other arc DE, that those must be equal as well. And we mean equal in measure. An arc measure is degree measure, okay? An arc measure is degree measure. So then just to bring it all together, if we have 2 chords of equal length in a circle, then the arcs that they cut have the same degree measure. And as for how one would prove this, well, let me now begin to make good on a promise that I made to you a while back, which was this, is that everything of any consequence that we'll discover about circles will follow from what we already knew about triangles. Let's begin with a set of constructions. That is, construct AB, AC, AD, AE. What are all of those? Radii. And it's true, we'll get isosceles triangles, but I don't think we'll actually need to say that. And what do you know about all the radii? They're all equal to one another, right? So all 4 of those segments are equal. Now what follows about the 2 triangles? They're congruent. By? Yes, SSS congruence. And it really shouldn't be a surprise, right? Because circles are just all the radii are equal. And so, of course, you've got lots of equal sides. And as a matter of fact, by SSS, the 2 triangles are congruent, which means then by CPCTE, those 2 angles at A are equal. But you know what? Those are central angles, right? And what's the relationship between the central angle and the arc that it cuts? They're the same. Okay, that was the fundamental assumption that we agreed to make. So each arc is equal to its central angle, but the central angles are equal, so the arcs are equal. I mean, it's as simple as that. I'm sure you can write it up. And it goes the other way around as well. Okay? That is, if you start with arcs that are equal in measure, like in this case, assume, or you are given that arc BC is equal to arc DE, then it will follow that the associated chords are also equal as well. So guess what? Construct triangles, prove them congruent. I'll let you think through the details, but that's how this goes. Here's a nice result. And this does come up explicitly in a number of myriad problems. So let's say that we have a diameter. In this diagram, diameter BC. Let us say that it passes through the midpoint of a chord that is itself not also a diameter. Okay. So in this case, the diameter BC passes through the midpoint D of chord EF. It will follow that the diameter is perpendicular to the chord. Okay. So the simple compressed version of this is that if you have a diameter that bisects a chord, it's also perpendicular to that chord. As for how this gets proven, well, guess what? You need radii, which those are equal to one another. Oh, and then you've got these two triangles, EDA and FDA, and they also have a side in common. So those triangles are congruent by SSS. No surprise, because, equal radii gives us equal sides. And then there's a maneuver that we haven't made in a while that I suspect you remember. What follows now about angles 1 and 2? They're equal, but they're also a what?
They form a straight line, so they're both right.
Yeah, so they're both right. That's the T theorem, right? They're a linear pair, they're equal, so they're right angles. Oh, but that's what we're supposed to prove, right? That BC is perpendicular to EF. See, it's just triangle congruence again, okay? And here's something cool, okay? Here's something really cool. The perpendicular bisector of a chord has to pass through the center of the circle, okay? So think about it like this, okay? So we started with a circle, and we weren't given the center. Okay, there was no point given here that is the center of the circle. It's somewhere, but it's not marked. Okay, and then into the circle we added the chord EF, and then BC is the perpendicular bisector of EF. Bisector because it goes to the midpoint, perpendicular because it forms the right angle. What will follow in this case is that the perpendicular bisector BC will pass through the center of the circle. That is, if you'd like to put it in another way, it will be a diameter, okay? It will be a diameter, which is really quite extraordinary. And I'll show you something that follows from this in just a moment. Now as for how this actually gets proven, well, there's more than one way to do this. I showed in my other class an indirect proof. We can talk about a direct proof if you like. Okay, so let's think about the triangles that are present here. If one looks at triangles EBD and FBD, they're congruent for sure, right? Side angle side. Likewise, if one looks at EDC and FDC, the two that are on the bottom, they're likewise congruent, also by side angle side. Oh, and then it follows, of course, got to use a lot of hash marks, that sides which correspond in the congruent triangles are equal. So it follows that EB is equal to BF. I guess I'm up to 5 now. It also follows that EC is equal to CF. What now follows about arcs EB and BF? Arc EB and BF. They're cut by equal chords, so they're equal as well. And look at but arc EC and arc FC. They're too cut by equal chords, so they are also equal. So now tell me about the entire arc BC compared to the entire arc B to C the other way around. They have to be equal because the parts of one are equal to the parts of the other. Oh, so I have divided a circle up into two equal parts. So what do those parts measure? They're semicircles. They're 180 degrees. Oh, but look at BC. Look at chord BC. It goes from one of the endpoints of a semicircle to the other endpoint of a semicircle. One of the proofs from section 1 says this has to be a diameter. This is one way to do this, okay? This is one way to do this. It actually seems a little complex to me. Let me show you the other way. With what I'm about to do, you might think to yourself, well, why did you show me that way? This way is easier. Well, maybe you're right. Let us approach this indirectly. This is the second way that this can be proven. Let us approach it indirectly. We wish to prove that BC is a diameter, that is, it passes through the center. So let us assume that it does not. That is, let us assume that the center of the circle, call it M, does not lie on BC. And then let us construct a chord that goes through both M and D. I can do this a bit better. A chord that goes through both M and D. Okay. Well, that's a chord now through the center of the circle, because we assume that M is the center of the circle. Oh, and also this diameter bisects a chord, because D is the midpoint of chord EF. And here's something that we proved just a moment ago, or whose proof we discussed anyway. If a diameter passes through the midpoint of a chord, it's perpendicular to it. So it will follow that this diameter through M and D must also be perpendicular to E and F. And hopefully you now see why this cannot be the case. Because we also have the angle that's formed by BC and, I don't know, give it a name, call it RS. That's alpha. That angle exists and has some measure, which means that now in a straight angle we have two right angles and something else. That means that a straight angle is greater than 180, which is impossible. And what led us to this predicament? The assumption that the center of the circle M does not lie on BC, but instead lies somewhere else. So it must be on BC. So that's the indirect proof of this. And again, here's what we've proven, that the perpendicular bisector of a chord, any chord, must pass through the center of a circle. Well, I think I basically have one slide twice over. I don't know why that's the case. So here's what I want to do with you, and I think this will be the last thing that I talk about. There are a couple of other results that you have to prove, but it gets proven with triangle congruence. So let me hop back over and talk about how it is that if we're given a circle and we have lost, as it were, the center of the circle, how it is that we can, through a series of constructions, reclaim that lost center. So let us say that we have a circle, okay? Terribly drawn circle, but there we go. And we don't have the center. We don't know where it is. We know it exists because by definition every circle has a center, but we don't know where to draw it. And let's say we wish to be accurate about this. Well, here's what we can do. Pick 2 points on the circle. Form the chord. These are all allowed constructions. The circle is just a collection of points. Pick 2. Construct the segment that goes from one to the other. Now construct the midpoint. We know midpoints exist. And then through that midpoint, construct a line that is perpendicular to the chord. And we know that we can construct perpendiculars. We've talked about this multiple times. So L is the perpendicular bisector of one chord. Let's do it again. Okay? So I'll make another chord. So there it is, a second chord, wherever you like. It too has a midpoint. And through that midpoint, I may construct the perpendicular to the chord. And I'll call that perpendicular bisector, let's say M. Now let's think about this. The result that I discussed with you a moment ago says this, that the perpendicular bisector of a chord always passes through the center of the circle. So L passes through the center of the circle, and M passes through the center of the circle. That is, both L and M pass through the center of the circle. Where is the center of the circle? Where they intersect, okay? Because what is intersection? It's a point on both, okay? It's a point on both. So if L goes through a certain point and M goes through that point as well, we have just said that that point is the point of intersection of the two lines. And that must be the center, okay? because the center is on both. That is, the unique point of intersection of these two lines must be the center of the circle. So the center of the circle has been found. It has been reclaimed. How do you get it? Two chords, and they're perpendicular bisectors. Mark where they intersect. That's the center of the circle. Okay, that's the center of the circle. And I